Thanks everyone for being here. So I'll try and keep the introduction short. Carol, she got her PhD from Durham University and then is an IFI fellow at MIT. She has won a large number of awards, including the Best Student Paper at SPIT awards, also from the Royal Society. And she's here to tell us about machine learning and cosmology. My personal connection with Carol is that I shared an office with her at IPMU when I visited last November. Had lots of good conversations, so I'm very happy for her to be here today. Thanks, Carol.
Thank you very much. Yeah, I'm super happy to be here. My first time in Arizona, and it really looks like a different planet. So yeah, it's been a lot of fun to explore. Enrique and Andres took me around yesterday, and sunset was beautiful. Yeah, super happy to be here. And I'm going to be here until next Tuesday. So yeah, we'd love to meet you all and talk about anything related to machine learning or cosmology, or like astrophysics in general. So please sign up on the schedule if you want to chat. I'm also going to be doing a workshop on generative models. And the idea is to start from the ground up. So if you don't know anything about machine learning, that's a great starting point. So that we'll take it from there and try to get you to train your first generative model. And then, yeah, hopefully that'll be useful for your future research. But today I'm going to talk more generally about my work on ML and cosmology. And I wanted to start with some context on where we're at in cosmology. And in particular, in what makes us very excited in terms of the data sets that we're going to be getting over the next few years. So there's a lot that we already have, like DESI, for instance. Today I'm going to talk a lot about DESI and galaxy clustering, but on all different wavelengths, we really are going to get a lot of new data. So we're very excited. We call this the era of big data in cosmology. But I think if we were to be honest, what we should say is that this is the era of big one-dimensional data cosmology. Because actually the data sets we analyze are not these beautiful high-dimensional pictures of the universe, but these very low one-dimensional statistics that we compute from them, right? So galaxy clustering is one example for the CMB, where we use two-point statistics, like the power spectrum or the two-point correlation function, to summarize all the information based on those very high-dimensional data sets. And we know that that summary is lossy, right? So there is information that we're losing by doing that. So what I'm going to argue is that we really need machine learning if we want to analyze the data in its full richness. And in particular, we need to also care about the astrophysics involved in these different processes. In cosmology, there's some, let's say, historical culture of thinking about astrophysics as our nuisance parameters in the analysis, right? So I think we're going to have to go a bit beyond that if we really want to understand the processes, for instance, like the 3D maps built by DESI, where we actually look at galaxy positions. So how do galaxies form actually will impact our analysis to the precision that we care about. But this is true for all major surveys. There's always going to be some systematic that we relate to galaxy formation or astrophysics that we really need to get to understand better. Now, what are the questions that we think about when we look at these different surveys? What are the answers that we're after? So first of all, we want to understand what dark matter is made of. So we believe there is 5 times more matter in the universe that doesn't interact with light and that we can see. And this is probably our most direct indirect evidence for dark matter, the Bullet cluster. You see these 2 galaxy clusters colliding against each other, and you can track where most of the matter is, which means just went past each other, where the dark matter is, through lensing. And you can see where the gas, deeply interacting through X-ray, stays in the middle. Right? So this is one of the most direct indirect evidence. And we believe this new survey is going to shed some light on what it's actually made of. On the other hand, we have dark energy and some very exciting new results from DESI. So Enrique here is very involved in this measurement. And the question is whether the driver behind the accelerated expansion is actually varying as a function of time or not. So this is the measurement from DESI. And if lambda CDM, so if dark energy was constant, it should lie in that point there. So W naught should be -1, WA should be 0. What DESI is finding is a slight tension towards different values, right? So obviously it's not yet a discovery and there's a lot to analyze, but it is pointing in an exciting direction, right? So we really want to find out whether that is the case. And more constraining power will be useful to do that. And obviously we also want to understand more about the early universe. So this picture from the cosmic microwave background, well, we can't see beyond that, right? We can't see an earlier universe than that. But the imprint of what happened before this period of inflationary expansion will actually leave traces in the large-scale structure of the universe that we believe we might be able to extract with these new surveys. Right, so why I think now is a good time to think about this intersection between machine learning, physics, in particular cosmology, and the new data sets and simulations. Well, because first of all, it's the first time that we have access to all of these, right? So we actually have observations that require a precision that we couldn't reach before. And simulations are also reaching a similar stage, right? Where they get to be compared with observations for really the first times of the last 5 to 10 years, to the degree that the precision of the observations. And machine learning can really help us make that connection between observations and simulations. But what I'm going to try to argue today is that we should view machine learning more as a new way of thinking rather than a tool, right? So it's not just a tool to make our life more convenient, but also as a new way of thinking about problems, and therefore as a way to open up new problems that maybe we just haven't thought about too much before because it seemed really just impossible. So as Pino was saying, so in the past, I've worked on many different fields during my PhD, all related to this kind of intersection, right? Where data comes together with simulation and compute, and also machine learning and statistics. So these are all topics I'm not going to talk about today, but please feel free to if you want to chat about them during the week, I'll be more than happy to. But I think maybe I want to highlight one of them that I think shows how this way of thinking about physics and machine learning can be very powerful, which is that of symmetry preserving machine learning, that you really need people coming from a background similar to physics to think about. So the idea is that we want to develop machine learning architectures that can preserve certain symmetries. So let's say in cosmology that we want to predict the velocities of galaxies. So if you have a point cloud of galaxies and you want to know how fast they're moving and in what direction. Now, if I rotate my galaxies, the velocities should rotate in the same way. They should be equivariant to rotations, right? Now, if you train a generic machine learning architecture, that won't be true. It might be approximately true, most likely it won't be true. So we're thinking about ways in which we can incorporate those symmetries in the architecture of the model so that we make sure they're enforced. And this is useful in other areas as well, like chemistry, where symmetry is also very important. But you really need to think about this intersection between machine learning and physics to get to things like this. What we've seen in the past is that if you actually incorporate those symmetries in the architecture, you need far fewer data to actually train your models. In particular, for very expensive simulators, that can make actually a big difference in terms of whether you can actually use the model or not. Okay, what is it that I'm actually going to talk about today? So I'll talk about these 3 topics, all related to generative models, which is also related to the topic of the workshop. But I'll talk about these 3 different areas that are really enabled by machine learning in cosmology. And in particular, I'll talk about how we can use ML to not only speed up our simulations, but also to enable field level inference so that we really do inference with the entire data set without thinking about summary statistics. And then I'll talk about 2 problems more related to high dimensional inference. So how do we infer latent variables, so things that we don't observe directly, from the observations that we have in these very high dimensional spaces. But first, I wanted to go back to Earth for a little bit and talk a bit about the progress in machine learning. I'm sure you've all seen images like this generated by AI, but over the years, I want to highlight how rapid the progress has been, right? So on the left-hand side, you have these deep belief networks that started in 2006, and they were struggling to draw numbers between 0 and 9, right? So this was already a very difficult problem. But you can see that very quickly, new models were proposed that could actually get around this. And just by a couple of years ago, diffusion models and GANs could get to generate these very high fidelity, high resolution images. And in the past couple of years, what we've seen is that it's not only that we can generate random images, but we can control the generation of images through text. So that was a huge deal, right? Where you can actually write a prompt and get an image, which is extremely hard, right? Because text is very high dimensional, images are very high dimensional. So obviously very high dimensional inference problems. And one of my favorite examples is this one called Genie 2. So this is a model that can generate a playable world. So you give it a prompt, like generate a game, a playable world as a robot in a futuristic city. And now you have a human playing a world that was generated by the AI. So this is very high dimensional because these images are like 1,000 times 1,000 pixels. And you have time as well. So yeah, if you think about sampling in MCMC sense, right? Even if you could describe this problem with an MCMC train, it would be extremely extremely difficult. Right? So it's enabled this kind of soft inference problems where you just have some soft relation between the left and the right-hand side, like the text and the world you want to generate, and data that you can learn from to train these models. An interesting example from the sciences is actually that of drug discovery. So people have been using these models to discover new drugs, in particular, given some properties you want the drug to satisfy. And I find this problem very interesting because they've moved beyond not just sampling these drugs, but also synthesizing them in an automated manner. So they have fully automated wet labs where the model designs a drug and actually tests whether the property is fulfilled. So this is very viable, right? The model can sample a drug and it may or not fulfill the requirement, right? The model might have made a mistake, but it can get a feedback loop from the automated wet lab to actually learn more about it. So these are very interesting problems where making a mistake is not a problem because you can actually verify it. I think in physics, it's important to think about this as well. What happens if the model makes a mistake, right? So how can we think about problems that can be solvable even if the model is sometimes wrong, but most of the time right? And in chemistry, it is definitely making a big difference. But I'm going to argue that inference in cosmology is kind of hard for two main reasons. So first of all, so far we only have one universe. So our data set size is 1. If you heard anything about machine learning, you've heard about big data, right? So yeah, obviously this is going to be a problem. And it explains why cosmology is so tied to Bayesian statistics, and it's been for a very long time. But that also explains why we have simulations, right? So we also can't poke the universe we get given. One experiment was run and we can only observe it from different angles. However, we can simulate, right? So this will solve the two problems. On one hand, that we can generate more data than just one universe. And on the other hand, that we can actually poke it, right? So we can change the properties of dark matter and see what the impact would be in the observables that we have. This is an example of such a simulation. So this is a Hydra sim called Eagle, run at Durham actually. And in the bottom, you have the evolution of the dark matter, so gravity only. On the other hand, you have how it interacts with gas. So this is basically where galaxies will form. Stars will form and will collapse into galaxies. And these simulations are obviously very, very expensive, but they serve the role of our theory models in a way because we know that the problem is fully nonlinear, so you actually need simulations to understand what's happening on these small scales and how galaxies form. But they also has become our testing beds. So any survey that you know of will use simulations to test their pipelines and make sure that the measurements are actually unbiased. Now, this also explains why simulation-based inference is so important for astrophysics. So in the past few years, there's been many, many works that put together machine learning, simulations, and astrophysics. We call this like simulation-based inference in general. And this is a collection of papers on simulation-based inference. These are only on cosmology and astrophysics. So if you look at the area of cosmology and astrophysics, loads and loads of papers. I think now there's a few on neuroscience and particle physics, but all those are on astrophysics. So really a lot in astro because of this confluence between simulations and astrophysics. Now, there's a separate section called applications to real data. This is already suspicious, right? Why do we have a separate section called applications to real data? So what are all the other papers doing if they're not saying something about our universe? Well, they're saying things about simulated universes because it's actually very hard to make it all the way to observations, right? With confidence. We know our simulators are not perfect. Therefore, in a way, we actually don't know how the models will behave out of distribution when the simulators are not perfect. So it's a bit sad, but so far, all the simulation-based things that we're doing is mostly on simulations. And doing this talk, I want to also make a case of how we're going to move forward, right? To actually say something about our universe, not just simulated universes. But one of the reasons why it is hard in cosmology in particular is astrophysics, right? So what's happening on a small scale? And this is an example from the CAMEL suite of simulations where people are running different hydrodynamical simulations. So these are making different assumptions about how galaxies form on very small scales. And in particular about two processes that are very hard to resolve, which is the feedback from AGNs and the feedback from supernovae. So things that are happening on really tiny scales that we can't really resolve when we run cosmological simulations of very large volumes. So here what you're looking at is the gas temperature and gas density as a function of redshift. So they're all starting from the same initial conditions, just different, what we call subgrid models, so assumptions about the small scale physics. And you can see by redshift 0, they look extremely different. Now, this is the gas temperature, so gas density is definitely not as bad as gas temperature, but you can see that different codes give different answers. So we really need to understand what the barriers are doing better if we want to use these very powerful inference methods. So what I'm going to talk about today is about this two-way route between simulations and observations. So on one hand, we want to use simulations to do some robust inference about what we observe. And in particular, I'll talk about how we can use generative models to make simulations faster, but also to do inference at the field level. Then I'll talk about this like higher inference, higher dimensional inference problem for reconstructing the dark matter density fields from the observed light from galaxies, or going all the way back to the initial conditions of the universe. And then I'll talk more about why, for future directions on how do we do anomaly detection in astrophysics using simulations as well, and how do we think about baryonic feedback going forwards. But today I'm going to talk a little about galaxy clustering in particular. So this is an image from DESI. Each point here is a galaxy, and it's zooming in a particular region that you can see by eye the cosmic web popping up, right? Because DESI is making one of the largest 3D maps, but right now the largest 3D map in the universe, millions of galaxies. And we use the clustering properties of these maps to learn something about the composition of the universe, to learn something about dark energy, dark matter, etc. Now, the way we do this usually is that we have a set of theory parameters that characterize the composition of the universe, like the amount of dark matter, properties of dark energy, like the equation of state, how it's varying as a function of time, or the properties of inflation, for instance. FNL is one way to characterize it. Then we have a form model, most usually observation theory, right? So some analytical expansion of gravity. So we think gravity on large scales is weak, so we can basically tailor expand it. And then we can make predictions for how some observables should look like. And in particular, we look at counts of galaxy pairs. So we take our millions of galaxies and we count how many pairs we have at any pair separation. So on the x-axis, you have pair separation. On the y-axis, you have probability of finding that number of pairs. And here you have the beautiful BO peak. Actually, I'm not going to talk about. But the idea is that we basically turning our 10 million galaxies into 10-ish data points. So we're summarizing that information by a lot, which makes it tractable, right? It means we can actually use perturbation theory to make predictions, and makes it accurate and robust as well, right? So we know that on large scales, this should work. Now, what we want to do is go the other way around, right? We have some observable, and we want to infer the theory parameters. So we want to get to these posterior distributions over the theory parameters, like the ones I showed for DESI before. So for that, we assume a likelihood for our observable, and we use perturbation theory to estimate the likelihood as well. Now, a lot of the work I've done in the past, together with Enrique Paredes here at Arizona, has been on replacing perturbation theory by simulators. So that we can go to smaller scales, use more information present in the field by using simulations. And right now we're working on this alternative clustering methods for DESI. The idea is that instead of using just galaxy pair counts, we will use other summary statistics of the galaxy field. So here you have some examples of them, just some random ones I'll highlight, like the wavelet scattering transform or void statistics. So we're just looking at different ones, right? The biospectrum, etc. And if you combine them, you can find a lot more constraining power on the cosmological parameters, right? Like here you see sigma 8, CDM. So this is work on simulations, right? So we know the true underlying parameters. This is not the real universe. This is one example of what happens if you try to extract more information. And right now, we're fighting against these fiber collisions. So if you've never heard about them, so this is, we saw them yesterday when we went up to the Mayal telescope, and they have some like real-sized fibers that are used in DESI to gather spectra of galaxies. If you never heard about the issue of fiber collisions, please don't ask about it. Your life would be better without them. But right now we're thinking about how do we infuse this kind of survey systematics in our simulations so that we can use these simulation-based models robustly for DESI.
But going beyond this, what I want to talk about now is how do we actually use the data directly? So instead of using summary statistics, how do we take the 3D galaxy positions and the inference directly with them? And the idea is that then you can find a lot more information in them, right? So this is completely made up. It's my very optimistic forecast of where I think the most fun will come from in DESI in the future, but it's not informed by anything, right? So this is just a visualization of what I think a lot of inference could do for cosmology. And what I'll talk about today as well is how we can go beyond just inferring a small set of parameters describing the overall composition of the universe and try to infer things like the initial conditions. So how the early universe looked like, or if you want to think about it this way, the random seed of our universe, so that we can reproduce the large-scale structure that we see with simulations directly. Right, but before I go into any of this, I wanted to start with a very brief introduction to generative models. And start with this 2D example. So here we have an example training set. Each point is one of our training samples. And we only have 2 dimensions. This is what is called the 2-moon problem for the structure it has. What we want to do with a generative model is to find a parametric probability distribution. So the parameters here are phi that will capture the underlying PDF, right? So it's now a continuous PDF, and we can actually find the phi parameters of this parametric model by just maximizing the likelihood of our training sample, right? So at first we will have some random PDF, but if we maximize the likelihood of our training samples, then we can find a good generative model of our data. And the way it would work is once you have a trained model, we can now sample from it. So you can generate novel samples. You have a PDF. So this will be, for instance, if you're trying to match human faces, but you can also evaluate probabilities, right? So if the model is well calibrated, it should be able to tell that that face has a high probability, whereas a human with 3 legs has very low probability because it's in the training set, right? And what's interesting about this is that if you think about the simulations that you have, your simulations are capable of generating novel samples, right? You can vary the initial conditions, I can vary the cosmological parameters, and I get a new sample. They're actually not capable of evaluating probabilities, right? You can't get a likelihood estimate for one of your simulations. So that's what the generative model is adding on to the picture, the ability to estimate probabilities, which means that we can generate novel samples very quickly, meaning we have fast emulators for our simulations, but because we can compute probabilities, we also have ways of testing our theories. So we can learn the likelihood from the data directly and use it to constrain theory models. So this is this dual thing between emulation and likelihood inference that generative models can add to the picture. And in particular, the most common generative models today for high-dimensional data sets is diffusion models. So you probably heard about them. You probably play with DALL-E or ChatGPT, generating images. And this is exactly the framework they use. And the way they work is actually very simple. So this is an example from a data set. What you're doing is you're just adding Gaussian noise to your data. So you're basically trying to destroy all the information and to the point that there's no information left, right? So you're bridging two distributions. One is a Gaussian white noise distribution, and the other one is your data distribution. So going this direction is very easy. We've all done it. Probably not wanting to, right? But we've all turned data into noise. Easy. The problem is going the other way, right? So this is what we call the forward diffusion, adding Gaussian noise. The question is, how do we do the reverse? How do we train a neural network to denoise very noisy data? So the neural network is going to get a noise sample and your data, and it's going to try to predict how much noise it was added to it. Right? So it's going to try to denoise it. And the idea is you can also prompt them, right? So this is not just a random image that's been generated, but it was prompted to generate a person half Yoda, half Gandalf, and I think you can tell what half belongs to whom. But the idea is that this bridge between the two distributions can be controlled by some external prompt. And we'll see how that can be useful for us as well. In particular, what we did is build on this idea about 4 point clouds. So in our case, we have a galaxy point cloud. So we don't have a pixelized image, but we have 3D points. So in this case, we're using a smaller set of points, and I'll tell you later why. So we have about 10,000 galaxies. And we want to be able to sample galaxy point clouds without running the simulation as a function of some theory parameters or the cosmological parameters. So here this looks very similar, right? So we have our simulated galaxy point cloud which lives in a cube, right? Because of the periodic boundary conditions. We're going to add noise to it, and we're going to train a model to denoise it. So it has a very similar structure to the diffusion model, but the denoiser is going to look very different, right? So in the case of images, for the denoiser, you usually use convolutional neural networks, whereas in our case, we have a point cloud. So the denoiser we used was a transformer. And it is at the prompt, so before we wanted to use text to generate images, now our prompt is going to be the cosmological parameters. So we're going to have a bridge between a Gaussian distribution of random points and our data distribution that's going to be controlled by the cosmological parameters. And that will allow us to also estimate the likelihood of our data as a function of the cosmological parameters without using any summary statistic, right? Just at the field level. Now, some fun things you can do with this, so you can fix all the random seeds in your diffusion process. So if you want to sample any simulation, let's say, you'll randomly draw some points from a Gaussian distribution, and then you use your model as a denoiser to get to a sample from the data distribution. And if you fix all the random seeds and vary the cosmological parameters, you can see how clustering is changing as a function of omega max and sigma 8 in this animation, right? So you can see how the clustering of galaxies is changing. So this is equivalent to fixing the initial conditions of your simulation and vary the cosmological parameters. Now you can use summary statistics to check whether your model is actually doing what you expect as a function of cosmology. Here we're showing the probability of finding k nearest neighbors, so one neighbor in this case. You can compare the diffusion model to the embodied simulation for different values of the cosmological parameters and see that it's actually doing what you will expect. You can also train it on velocities as well, so you can use the galaxy velocities as well and look at things like mean relative velocities between any two galaxies as a function of pair separation, and again see that the model is actually doing the right thing. Now I think this is interesting because physics is a very good testing ground for this kind of generative models. In particular, because we have all these very well understood summary statistics that are very stringent test of the generative model. If you think about human images, we don't really have a power spectrum as a function of age for human faces, right? So it's actually very hard to quantitatively assess a generative model for natural images. Usually, even like sometimes you have to get people involved, right, to really look at the images and tell you which one looks better, because we don't have amazing metrics to distinguish them. Whereas in physics, we usually have pretty good metrics to be able to tell whether the generative model is doing the right thing. Now, as I told you, we not only care about the ability to generate, but also about the ability to estimate likelihoods. So here I'm going to show you how we can use the diffusion model to estimate probabilities. So we can estimate the probabilities of a given galaxy point cloud as a function of some theory parameters. We can use that as our likelihood and then sample the posterior of those parameters. So here you have an example, again, on simulations. So these are simulated galaxies, and we compared pair counting to the diffusion model likelihood. And this is only for about 10,000 galaxies. So if you use the heaviest 10,000 galaxies, you can get things like this for omega matter and sigma 8. So the matter energy density in the universe and the initial completeness of the galaxy distribution. So you can get a lot more information by using this diffusion model likelihood that you could by using pair counting. Now, this is only with about 10,000 galaxies. So
for this one, the data vector is XYZ positions of 10,000 galaxies?
That's right. Yeah. So still pretty high dimensional, but ideally we want to go to millions of galaxies, right? So we're still far from the millions of galaxies. It's a lot we need today to be able to scale it up. In particular, because you need a lot of GPU memory to be able to do this with 10,000 galaxies. But yeah, we're thinking about ways in which we can actually make this work for about 1 million galaxies. And I think then this difference might scale even more if you have millions of galaxies. But the idea, this is already more than doubling the survey volume, right? So obviously, in number of dollars is this may increase. But something else we looked at is whether these generative model likelihoods are actually more robust than posterior models. So what do I mean by that? So what you could do is you could train a convolutional neural network directly to estimate the cosmological parameters, right? So you put your galaxies on a mesh, you have a density field, and you try to estimate the cosmological parameters. You can see here an example of predicting sigma 8, the true versus predicted, and comparing this convolutional neural network. So I'll call this a posterior model because it's trying to directly infer the cosmological parameters versus the diffusion model likelihood. So I want to highlight this difference between posterior and likelihood, right? So the diffusion model is trying to model the likelihood, the CNN is trying to model the posterior directly. And you can see that They perform very similarly, right? So maybe the diffusion model is doing slightly better, but they're really very similar. But if we add some noise to them, this is a slight amount of Gaussian noise to the two of them, then you can see that the CNN becomes very biased very quickly. So there's a tiny amount of noise. The power spectrum will not change at all, right? So you'll hope your model is robust to change like this, right? If it's not, it means you're probably in trouble with the difference between simulations and what we actually observe. Right? So likelihood models seem to be more robust to model misspecification than posterior models. And you can see if you're in more noise, this becomes very, very clear. Right? So I think there's reasons why thinking about likelihoods is usually a better idea than posteriors. Now, why are people not doing that? Well, because it's harder to, if you think about P of x given theta, x is very high dimensional. You have millions of galaxies. Theta is very low dimensional. It's the cosmological parameters. So it's easier to estimate P of theta given x, but it's less robust. So just to summarize this section, so these generative models can be very fast emulators. So if you compare, for instance, generating these dark matter density fields, you can generate them in 6 seconds per simulation versus 40 million CPU hours, right? So it's definitely much cheaper. But they can also allow for parameter constraints. So they're not just fast emulators, but also they're very good likelihood estimators as well at the field level. So without using any summary statistics at all. And the hope is that that will allow us to really make the most out of these surveys and maybe turn slight tensions into more well, stronger evidence towards maybe that evolved dark energy as one example. I want to move on to a different set of problems, and these are more related to this high dimensional inference problem. So this was work led by 2 students at the CFA, Corey, Francisco Clark, and Victoria Ono. And the idea is that we wanted to debias galaxy clustering. So in galaxy clustering, you have some observations of light coming from galaxies. You have here an example of putting those galaxies on a mesh on very small scales. We'll talk about this later. But you want to infer the underlying dark matter distribution that you can't observe. So in simulations, we can jointly model them. So this obviously comes from a simulation. But the idea is that we want to be able to sample these dark matter cosmic webs given the galaxy distribution. We want to sample because this is a one-to-many mapping, right? There's potentially many dark matter distributions that will be compatible with the galaxies that we observe. We want to capture the uncertainty in that mapping. So we can use diffusion models to do this as well, to solve these high-dimensional inference problems. You have here an example of the model trained in simulations on the camel simulations again. And this is one sample from the model, right? So it's definitely generating a cosmic web that looks like what we would expect, right? Filaments, nodes, etc. Some of them will look right, some of them will look completely wrong. And I'll show you later what happens when you draw more samples to capture the uncertainty in this mapping. Again, you can use summary statistics to check whether your model is doing what you expect it to do. So here you can see the power spectrum. You see the power spectrum of the galaxies that you start from, and then the sample power spectrum. So what the model has found in the dark matter cosmic web. So it seems to be doing the right thing. Now, if we think about sizes, what I was showing you was 25 neoplastic average boxes, right? This is tiny in cosmology. And if you think about DESI, the volume of DESI is much larger than that. This is not scale, because if I do a scale, you wouldn't see camels, right? So we have this issue of hydrosims are extremely expensive, right? So we want to self-consistently model galaxy formation and dark matter. We can only do that on very small simulations. However, we want to do inference in cosmological scales, right? So how do we bridge this gap between what we can simulate and what we want to do inference on? So my idea is that because this mapping is very local, perhaps we can learn this mapping from very small simulations and then do inference over these large boxes. So that's what we tried naively. So we can use larger simulations for testing. So this is TNG 300. Now we're not using it for training because we only have one TNG 300, right? Whereas in camels, what we can do is we can vary the astrophysical parameters to capture the uncertainty in the subgrid physics. And we have a lot more simulations that we can use for training, whereas, yeah, TNG is just one. But we can use it for testing, right? So you can see here the size of the camel simulation in red and orange. So they're very, very small. If you look at the void, it's basically the size of one void in TNG 300, right? So very, very small. So this is the true underlying dark matter distribution. And this is what the model predicts for one sample, right? So if we draw one sample, and if you look at the power spectrum on large scales, it is actually very, very close to truth. So this idea that you can learn the mapping from small scale simulations and apply it to larger scales seems to be working. Now, what is happening in the void region? So if we draw many samples, you can see here how different samples look like. So in the cluster region, where you have loads of galaxies, your constraints are very good, right? So these filaments are actually very well constrained. But in void-like regions where you have very few galaxies, you have very little constrained power, right? So it's basically sampling from the prior. And the prior is cold dark matter. So it's basically sampling cold dark matter cosmic webs that could be living in that void. Now that's exactly what we wanted, right? We wanted a way to model the uncertainty of our model. So it should be uncertain in void-like regions, but it should be pretty certain where we have a lot of constraining power. On one hand, we found that we could generalize the larger volumes by training on this very small scale simulations, because the uncertainty here is more dominated by the sparsity of the galaxies, the fact that the galaxies are very sparse. And what I haven't told you is that we were also using a different galaxy formation model. So this model was trained on the Astrid simulation. So if you remember that video I showed you earlier, TNG was one of the models. Astrid is a different model. So it's different assumptions that go into the galaxy formation physics, but it was being tested on TNG. So it was generalizing well across separate models as well. It was important to show that what you're doing is at least kind of robust. That it doesn't mean everything, but it's pointing in the right direction. And right now we're working on applications to galaxy surveys. So this is from Cosmic Flows, a very small survey. And this is the 3D reconstruction. So here you can see one posterior sample. So again, it's very small. You can see it's like 40 megapascal coverage size, so very small volume. And here you can see the posterior mean. So if we draw many samples and take the mean, these are the structures the model is very confident about. So these very large filaments and some of the substructure is actually very well constrained by the model. But there is a lot of it that is actually uncertain. So this is, you can use generative models to capture the uncertainty in this very high dimensional mappings. Now, again, summarizing, so this is actually a very hard problem to solve without machine learning because it's very high dimensional. So you will be sampling over 20 million dimensions. And a sample will cost 6,000 CPU hours, right? If you really had to run a hydrosim to draw each sample, it'd be extremely expensive. And it was interesting to find that actually this mapping can be robust to galaxy formation uncertainties because the sparsity of the galaxies is dominating here. Not because it doesn't matter, but it's not the dominant source of uncertainty. Another interesting problem that very related is that instead of reconstructing the dark matter today, can we reconstruct the dark matter back in time? Right, so this is what I was talking about earlier in terms of reconstructing the initial conditions or the random seed of our universe. And that's interesting because if we can actually reconstruct the initial conditions, it's not that we're just reconstructing the dark matter at a given time, where we reconstruct the entire formation history, the velocity of the galaxies, anything you might be interested in. And this is an example of just the simulation running backwards, which is pretty weird if you layer run to see things drift apart if you've heard of many of these videos before. So the idea is that you have some set of initial conditions, right, with random seeds that are drawn from a Gaussian random field. So we believe the early universe was very close to a Gaussian random field. And that's the way we draw initial conditions for simulations. And then we have a set of theory parameters or cosmological parameters that will determine the evolution of this field. If we put them together on a simulator, we get some final observed field. Ideally galaxies. Now we're going to talk only about dark matter to make the problem a bit simpler. But the idea is that we want to go, again, we want to go backwards, right? So we want to go from the observations today, something like DESI, into a joint posterior of the initial conditions and cosmological parameters, such that we can draw simulations that look like what DESI sees. So usually we run simulations with random universes. What we want to do is a constrained simulation. So we want to run simulations that actually look like DESI, so that will generate the right large-scale structure that we see. Now, again, it's a problem because it's very high-dimensional inference. So for something like DESI, we will want to do something like 2,000 cubed pixels. That is a lot. The cosmological parameters, again, are pretty low-dimensional, and we can take advantage of that. But the initial conditions are very, very high-dimensional. Now, what we did is take this joint probability distribution and split it into two conditionals. So on one hand, we will have a generative model trying to sample initial condition, marginalizing over the cosmological parameters. And on the other hand, we'll have a simpler model, normalizing flow, just a simpler model that can work on a smaller number of dimensions, sampling the cosmological parameters only, given final and initial conditions. So you can couple the two models together to get to the joint probability distribution. And this is an example where you have the true initial conditions and the final observation. And this is what the model would do when trying to reconstruct the initial conditions. So here we're sampling this posterior distribution and running different initial conditions with different cosmologies forwards. And what you see is that the finals agree very well with what you expect to observe, right? So you're jointly constraining the random seed and the cosmological parameters to be able to run simulations that give you the same large-scale structure. Now, the way we do this is very similar to a diffusion model, but not quite. And it's not quite because if you look at how a diffusion model will look like in this case, you will start from some random white noise, and then you will learn a stochastic differential equation that will take you to the initial conditions. That's what a diffusion model is attempting to do. But here we have a starting point that's already very correlated with initial conditions, right? We have the final observation. So instead we use a different set of models that can actually take advantage of that. And I'm gonna talk more about them in the workshop if you wanna come tomorrow. But it's very similar ideas that adapt to any bridging of distributions. So a diffusion model is attempting to bridge a white noise distribution into your data distribution, whereas you can more generally think about how to bridge any two distributions. And in particular, if you can take advantage of the correlations in your data, this mapping can become much simpler. So if we start from the final observations, this mapping is already much simpler and you're already very close to your data distribution. Yeah.
Can you go to the previous slide for just 1 second? So I'm missing something. So you've split the probability distribution this way, but when I look at the term in purple, right, like why isn't like
it's marginalized over cosmology. So your training set is actually varying cosmology as well, and then you're learning the marginal.
Oh, okay. And so there's a prior in that purple that's
yes,
marginalized.
there's a prior that's being marginalized over. That should be
Okay, now
consistent
that's what I
with-
was missing. Thank you. Sorry.
Yeah, no worries. Right, so yeah, we can use these interpolant models, which are kind of a generalization over diffusion to bridge any two distribution, and that actually made it much more efficient than if you were to use a diffusion model. So these are all differences that we'll talk about tomorrow, but the idea is that now, if you look at the zoo of generative models, they may seem completely unrelated, but they're actually all very related. And it's all about how do you bridge any two distributions. You start from interpolants, you can actually derive all the other models from it. So they're actually all very related. But if you have some structure in your problem that you can take advantage of, it's always a good idea to do so. Summarizing this section again, we're sampling over an insane amount of dimensions, right? So we're talking about 100 million dimensions here, jointly with the theory parameters. Now, why would we want to do this? What can we do actually with the random seeds in cosmology in particular? So I think there's several things why this is interesting to do. So first of all, because we can reconstruct all the latent variables. So it's not just the dark matter field, but the entire formation history, velocities, etc. And we can use them to constrain inflation as well. So now we're getting this, we're removing gravitational evolution from the picture, and we're trying to get back to how the early density field should have looked like and use it to constrain inflation as well. But another reason why I find it interesting is due to interpretability. So in particular, if you're using machine learning to get some posterior distribution, first of all, I already showed you that targeting posteriors is kind of dangerous. You can get bias constraints very quickly. But then you also want to have some measure of goodness of fit, right? How well is my model doing when I compare it to my observations? And actually, if you have the inferred initial conditions, you can make very accurate tests without cosmic variance. So you could, for instance, predict what you shall observe between the cross-correlation of your simulated galaxy density field and the lensing from the cosmic microwave background, for instance, right? Without cosmic variance. So that could be very, very powerful. So it's not just because we can reconstruct a lot more if we actually infer the initial conditions, but it adds a lot of interpretability to the problem. Right, so I told you about the part 1 and part 2. So generative models and what they can add when put together with simulations in terms of likelihood, field level likelihood inference, but also reconstructing high-dimensional problems. And I want to talk about these other two topics, and in particular, how we think about anomaly detection in cosmology and what machine learning can do for us here. What do I mean by anomaly detection in the first place? So it's finding weird things in our data, right? And the way we're doing cosmology right now, I think, is mainly through two different routes. So one of them is by comparing the early universe and the late universe. So this is an example from H0, so trying to infer the expansion rate of the universe from either data sets that look at the early universe, the CMV, or data sets that look at the late universe, like supernova issues. So here you can see as a function of the year of publication. So the two used to be very consistent, actually. But you can see as the data got better, they started to drift apart. So this is what we call the H0 tension. The fact that these two measurements don't seem to be compatible. But if we had the right theory for the evolution of the universe, you will hope these two will be compatible, right? So there seems to be an issue here. So there's one way in which we try and find anomalies. The question is whether machine learning can actually make this tension worse or better, or let's see what happens there. And we've been doing that for clustering, for instance, so comparing the early universe to the late universe. And in this paper here, for instance, we show that if we use simulations and machine learning to set priors on galaxy formation, we can actually find tensions on parameters like sigma 8. So if you look at the green, that would be the CMB, or the early universe. The gray is the analysis we did without any machine learning or any simulations. And then the red and blue, what happens when we used simulations and machine learning to set priors in galaxy formation parameters. And you can see that the tension became much more apparent. Whether it is actually there, that we still don't know, right? So DESI will have a lot to say about that. So this is still the predecessor to DESI, BOSS. It's the much smaller volume. The other route we have for finding anomalies in cosmology is parametric extensions. So there's an example from dynamic dark energy. So we have to hypothesize some parametric extension, like how dark energy equation of state should vary as a function of time, and then we can constrain it and see if it's compatible with it being zero. Right? So that's the second route. And the question is whether the machine learning models we're developing will extract more information, but do so in a robust manner, right? So in a way that we can actually believe the error bars that we're getting from them. That's still an open question. But this route is very tricky, right? Because if you start thinking about parametric extensions, you can keep going, right? Like there's going to be a lot of them to look at. So I think it'd be very interesting if we could extend previous challenges. So this is a paper from the Beyond 2 Point challenge, where we basically analyzed some blind mock data to show whether other methods beyond 2 Point were actually capable of recording true cosmological parameters. It'd be interesting to see if we had simulated different extensions to lambda CDM, whether anyone will have noticed that it wasn't lambda CDM. Right? Because my suspicion is that many of these analyses will actually not even realize that it's not lambda CDM, right? We'll just get some constraints in omega matter and sigma 8, call it a day, without even realizing that the underlying model is not compatible with our simulations. So I think it'd be very important to have a mock challenge going in that direction. But in particular, what I'm thinking in that direction in terms of machine learning is how do we think about simulation-based inference when we know our simulations might not be like our observations, right? And in particular, how we can put together the observations and the simulations with the inference frame. So classifiers will play a big role where you're trying to train a model to distinguish simulations from observations. Right? So if your simulations can't describe data, the ML model will really struggle to tell them apart. But if they look very different, it will very quickly achieve a classification accuracy of 0.5, right? Sorry, of 1, because it's very easy to tell them apart. So you can include this in your inference loss function. So for those familiar with simulation-based inference, usually what you're trying to do is you're trying to train these posterior models where you have a summarizer, so a neural network that takes your high-dimensional data and projects it into smaller latent space. And then you're trying to infer the parameters of interest, like cosmological parameters. So this part of the loss function is making sure that you can get summaries that are informative of the parameters of interest from your neural network. So this is the usual loss function. What I'm trying to do is add this adversarial loss function. It's also telling the model whether the simulations and the observations should look very similar in this latent space or very different. So you're trying to poke it to either be more robust, so it is lambda is negative, you actually tell it, remove any discrepancies between simulations and observations. So that becomes more robust, right? You're only using the information that they have in common, and also the information that is informative on the parameters given the simulations. Or you can ask lambda to be positive, and then you're looking for the most anomalous summary statistic, right? The most surprising, let's say. The one that is constraining of your parameters, but the model can very easily tell apart simulations and observations. So you can play around with these things to either make the model more robust or more anomalous. Now, I think a good question is what makes an anomaly in astrophysics interesting, more generally, not just for cosmology, right? But when we talk about anomaly detection, what do we mean? Because finding something rare is not everything, right? It's finding something physically interesting. So how do we tie anomaly detection with what we define as physically interesting? I think it's a very challenging thing to do. And it becomes a representation learning problem. So in what representation does the anomaly become interesting? So I'm working with different groups. So on one hand on supernovae science, so supernovae light curves, in particular for LSST. We want to know what supernovae do we want to follow up with different instruments to get a spectra. So which ones are the most interesting to follow up? And we're looking into methods in which we can use simulated explosions to determine what supernovae will actually be interesting. So given the physics that we know, how do we learn a representation with all the different simulated energy sources live together that will tell us which ones are the most interesting to follow up? Some other interesting ideas is to use text to actually enhance the representation of astrophysical sources. So this is working with X-ray data, with Chandra in particular, where you have some event files, so the X-ray data, but also some text associated with it that comes from a proposal or a paper that some astronomer wanted to do with it, and whether we can use that text to actually enhance the representation and find more interesting anomalies. So this all is under the same thread of how do we define in what space are the anomalies actually interesting. But in cosmology in particular, going back, I think there's going to be always the question of whether the anomaly we're finding is new physics or just pesky baryons or some systematic in our survey that we didn't account for, right? And we know that the complex physics of galaxy formation can actually mimic the physics that we're after, right? So if you look at alternative dark matter models, you can always find similar signatures coming from galaxy formation on small scales. So will we be able to distinguish them? That's very unclear. It's a very ill-defined problem, right? How do you distinguish one segment from the other? So I think one question is how do we build more predictive hybrid simulators, right? And the question of whether we can build hybrid simulators where you have a machine learning model be your subgroup physics that is trained on a smaller volume, higher resolution simulations, kind of a Matryoshka of scales. But yeah, these are all other questions because high resolution simulations are obviously also very expensive. So generating large training sets is also challenging. But I think there's a lot of architectural development on the machine learning side that we also need to do to decrease the number of simulations that one actually needs for training to make it much smaller. I'm part of this learning the universe collaboration. So goal is kind of to move in this direction, right? To make more predictive hydro sims that don't depend so much on the particular subgroup physics. Right, so this is kind of the overarching theme, right? How we use simulations and observations. But I wanted to take the last few minutes to also introduce a new question, and is something that I think a few years ago no one would have taken seriously. I definitely wouldn't have taken it seriously. And is what is the role that more general AI scientists could play, right? And the question is whether an AI scientist is actually going to be closing this loop. In particular, I think this question is now not too crazy because we've seen how AI has changed more generally. So if we go back to the medieval times of machine learning, 2022, right, a long time ago, the best AI was AlphaGo, right? AlphaGo was an AI that could play Go and defeated a human for the first time in, like, well, the best human at Go for the first time in 2022. And it was an amazing achievement, but this AI could not do anything else, right? It could only play AlphaGo. So if you ask it any question about physics, it will tell you, oh, move the wine to B3 or whatever, right? It did not know anything else about Go. However, today, we have AIs that can actually solve a plethora of very different tasks, right? So they seem to be getting closer to this idea of artificial general intelligence. So AIs that can actually solve many different problems with just the same model. So then things become interesting. In particular, if you look at benchmarks, so this is the year since the benchmark was introduced, and the score relative to human performance. So this dashed line is human performance, and these lines are different benchmarks. So you can see very quickly every time we introduce benchmark about, I don't know, theorem proving or physics questions, whatever it is, very quickly the AIs become very, very good at it. There was one that they were really struggling with, this ARC AGI. If you look at ARC AGI, it's actually a benchmark about common sense reasoning. So the data looks like something like this. So the AI gets given an input like this and an example output. So it's like pattern reasoning. So a child, like a 4-year-old, could actually do really well, like a small 4-year-old, because it doesn't require any previous knowledge. It's just about common sense. But actually, AIs were doing terribly at it. Right? But only a few months later, well, maybe a few years, let's call it a few years, you can see that the latest 01 or 3 models from ChatGPT are actually doing really well. So the latest AIs are actually doing really well at this kind of common sense reasoning. But one of the things to learn from this is that if we find meaningful benchmarks, AIs actually become better at that task. So if we want better AI scientists, we do need better benchmarks to actually measure how well are they getting close to actually doing science. So in particular, I'm working on using LLMs for discovery in cosmology, right? So whether they can do things like resolve the Hubble tension or find models of dark energy that will explain the Desi anomaly. Obviously, there's a lot going on for an AI to solve this problem, and the idea is whether we can evaluate their skills on very different levels, right? And coding plays a big role here, right? Because if you work on any beyond lambda sphere models, what you need to do is implement modifications to gravity on Planck, on class, common CMB code, right? So that's what we're working on currently, on testing their ability to actually implement beyond lambda sphere models on class. Whether they're ready to do this today, probably not, probably they're very far away. But having a way to measure how far away they are, I think would be actually very, very useful to see what will happen in the future. But yeah, I think I'm running out of time, so I'm going to end here and just leave you with this summary. Thank you.
Questions?
That last one about the pattern recognition, like 2 slides ago. What's the y-axis on the right-hand side? Is it actually defeating humans now, or?
Oh, you mean the human performance?
Well, you showed that it's rapidly improved.
Right, yeah.
But where is it now on the left-hand side?
Yeah, I don't know what the average human performance is. I think it's very close. So again, you have to take into account that this is average human performance. So it's not the best human at this, right? So the same with this y-axis here. I mean, it's very impressive that one model can surpass the average human on anything you want, right? Because the best human will never be the best human at everything. You'd be best at one thing, right? Whereas this AI can actually be at least the average human at those things.
Can you elaborate on, I think, the last slide, or the last but one slide?
Right.
Yeah, that one. So on point 2, implementing beyond LCDM models.
Mm-hmm.
So is the idea here that the AI is actually doing the modifications to class, or?
That's right. So you give it the modification you want to set, you give it the papers that describe those modifications, and then it modifies class. And it definitely gets compiled, which is already, I mean, if you try to modify class, I'd be very surprised if you go to compile on your first go. So that's already very impressive. But yeah, the idea is that then you can compare the constraints from those papers with the ones the LLM gets and see if it gets any close to them. And what I like about this problem is that you have a very concrete metric, which is whether you're resolving the Hubble tension, right? The same with the sigma tension, etc. So you can actually use that to do reinforcement learning in the model, right? So to tell the model, okay, the implementation, like the physics models that you're sampling, the theory models that you're sampling, are they getting closer to resolving the Hubble tension or not? So you have this very strong signal to something in that direction that you can potentially use.
Is this, sorry, is this linear scales only, or does the AI actually recognize that at some point, oh, I'm going into a modified gravity theory and now I can't use nonlinear structure growth anymore? Or
No, right now we're telling it you have the CMB. It's only working with the CMB.
Alright.
You don't have to worry about all these things. So we're starting simple, right?
got it.
And
Thank you.
then Eduardo and Alan.
I was just curious, could you talk a little more about the hypothesis generation part?
Right, so that's where the hope is that, because obviously you just ask the model to come up with, just give me ideas, like you'll get rubbish, like you won't get anything interesting. Oh, sorry. Right. But the hope is that if you actually have a metric that you can use to force the model to move in a particular direction, that you can get more interesting things. But that is to be seen, right? Like these models are probably not that good at hypothesis generation, but it'd be good to have a metric on them.
But you have a couple of examples there. Are those benchmarks that you hope the model generates, or why are those examples up there? I guess the self-interacting.
Oh no, they're just example
Oh, okay,
hypotheses
okay,
that
fine.
humans have come up with.
Okay.
Yeah. No, it's not the model has. But if you ask the model, it will give you some some early dark energy. It will just make up a new potential. But that's not that interesting, right? We can do that too. But how do we measure interesting is also an interesting question, right? Like, how do you put a metric of any of these things is already a very hard problem.
So when you were reconstructing the matter distribution and you trained on one hadron rather than another, I can't remember which one you trained on and which one you run. So it looked very good, but like the thing that you see by eye is kind of like the large scale distribution, which that makes a lot of sense that would be pretty robust. If you look at, say, like the halo mass correlation function or the halo gas correlation function, like do they look the same, or do you just or do you just get back out the density the gas density profiles from your training data and they differ from the
Right, so here we don't have gas, right? We only have either the galaxies or the mass field. But you can look at the halo masses, for instance, the inferred halo masses, right? And what I thought would fail miserably is clusters, because on these like very small boxes, you can't build very large clusters. You don't have enough matter to actually build them, right? So your training set has very few of them, maybe a couple, but not many. But actually, it didn't work too badly. So the scatter there is high, right? So the model is uncertain about those halo masses, but it's not biased. It's just uncertain. So that's not too bad. I'd rather be uncertain than biased, right? But to me, it wasn't obvious that scaling to larger scales will actually work, because yeah, the problem is local, but how local? Is 25 megaparsec local, or is it?
right?
But again, it's because of this sparsity of the galaxies, right? If you try to do this with gas, it'd probably not work.
Alan?
Yeah, sorry if I missed it, but I guess when you were trying to do the field level inference to recover the initial conditions for the large scale structure, in your input data, for example, from these simulated galaxies, were you only using 3D space information from the galaxies? Right. Okay. So then I'm not sure if you have a good answer for this, but a very naive question from me would be, we know that in those large surveys of galaxies, not only do we get three-dimensional space information, coordinates, but we also get fluxes, colors, and we can claim that we can infer stellar masses and star formation histories of those galaxies. So I naively I would say yes, we claim that we know them, but in principle, if at all possible, I would like to make use of those informations as well in the field level inference. But I guess it's still a big problem for astronomy as a whole field to figure out how to connect, say, our theory of like starting from dark matter halos to forward model these all these properties. So I guess I was wondering, firstly, using, I guess, whatever machine learning tools, can we address this problem in a different way than previous efforts? And secondly, if this problem has to be addressed by either observations or models that are not so machine learning, what do you think we should get from all these other efforts other than machine learning?
Right, so yeah, your question on what we can simulate is different from what we can observe, right? So we always have this issue of like, okay, in simulations we have stellar masses, but we can't actually observe that, right? We observe velocities or whatever it is that we observe, right? So there's always this problem of how to connect the two in a way that is sensible. What I mean by that is that, yeah, we have models that can go from one to the other, but they're making very strong assumptions. And we're not varying those assumptions at all. So that's what camels is attempting in one way. This is not the best way to do it, but if you just vary the separate physics parameters, at least you get some sense of the uncertainty in your theory model. Now, you probably shouldn't vary them blindly like Carlos is doing, right? It's probably a bad strategy, but at least it's one step in the right direction, right? Try and capture the uncertainty that you know you should have. So if you want to do this mapping between what you're going to simulate and what you observe, at least I hope you have some ways of capturing the uncertainty in this mapping, right? Then you can start using it. But I think until then, I mean, you can test how non-robust it is, right? Probably by changing the models slightly and seeing how they stop working, right? So yeah, at least I would like to see models that are more flexible. Now, whether ML is the right way to do that, I'm not sure. I think what we want to do is use ML to constrain the physical models behind it. So we want more flexible physical models that we can use ML to learn more from them when we compare them to observations. That we might point to. But yeah, ideally we could use that information, that'd be great. So we're working on right now like galaxy peculiar velocities, right, where we can use them because we get some measurements of peculiar velocities for some galaxies. And obviously that's very correlated with black matter field and the initial conditions. So we could use them, that'd be great too. Now how robust it is, yeah, that's a different question.
Yeah.
On the point you just mentioned, when you say physical models, is there an implicit sort of meaning built in that it needs to have fewer parameters than any machine learning model is?
What do you mean?
And it builds into the idea of interpretability as well. Like when you say physical, sure, you have the physics sort of laws that we have, but let's say you come up with some flexible model that fits the data.
Yeah.
Do we expect them to have sort of fewer parameters or way more, or do we need like 100,000 parameters that these models have? Where are you on that?
Yeah, I would say to me, a model is interesting why it allows you to test a new hypothesis. And for instance, if you think about galaxy systemly bias, right? Does galaxy clustering depend on the environment around it? Now, how you parameterize that, I don't care. As long as you have a way to say like, oh, wow, yeah, it seems to depend on it, right? As long as it builds on a story that tells us something about the physics behind, how you parameterize it, I think it's not that important. So whether it's more empirical or less, I think, at least I'm not too bothered by that.
Okay.
At least it's telling us something about the physics behind in some way. Now, if it's completely disconnected and they don't have any meaning, and that's not very useful, right?
Right, running a little bit late, so one more question and then, yeah.
So just a short question. So you mentioned about there's a classification tool that can tell you, that can distinguish among observation and simulation. Then I'm wondering, like, would you like try to make the model more interpretable so that we know why, like, for example, I made a simulation and it's 50% to be true, like probability. Then how do I improve it to maybe 80% or 90%?
Yeah, that's a great question, right? How do we get a feedback loop of like, okay, the model is not working, but how can we improve it, right? And to me, so when we talk about interpretability, I think we don't really know what we mean because is even interpretable for humans? It's hard to tell, right? Is a simulation interpretable? Well, probably not. But why? Because we like two-dimensional things, because we have eyes. It's all hard to tell, right? But to me, interpretability really ties into what you're saying is how do we develop new hypotheses? That is, to
me what becomes interpretable, right? Once you can develop a new hypothesis that shows that explains the observations better, that's moving into what I would say an interpretable direction, right? Because it's helping you develop new physical models. Now, how to do that to me is unclear. So one of the things so this is still in a very like time model phase, right? The stuff I'm doing with this like regularized simulation-based inference in a way. But one of the things you can do is now you can learn these two different summaries, like the most robust and the most anomalous. And then you can see what features of the data are generated by either of the summaries, right? So if you only have, so one example that I'm using is the power spectrum with a bump, right? So if your simulations are just power spectra, but your observations have a bump, now if you do the most robust thing, it will forget about the small scales, right? Whereas if you do the most anomalous thing, it will really pick on the small scales. So now, yeah, you can find ways in which you could pinpoint that, right? So you can say, okay, this is where it's failing, right? Now, obviously, in a high-dimensional setup, it could be that it's like, I don't know, the low-density regions versus high-density. So how you figure that out is still hard. But there are ways in which you could try and attribute how the two summaries differ to features in your data.
Almost sounds like, here's a metric. We should just let an LLM loose on this subgrid physics modules of a hydro simulation and see how it does.
Right, but then you still have to interpret it,
We
right?
just have
Which
to interpret
is,
it, at least.
but at least, yeah, we'll try to
Simulation
correct
is-
it. Yeah.
All right. So Carol will be around the rest of this week and also Monday next week. There's plenty of space in her schedule. So in the email you all received about this lecture, there's a link to access her schedule. So please sign up and talk to her. She does an amazing variety of different things, all related to machine learning. So I encourage all of you to take advantage of that. As well, the workshop tomorrow on generative models to do all of this magic you learned about today will be at 1:30 in room N305 in Stewart.